Hello and welcome back. The subject of this video is to introduce you to fluid statics. So a fluid is something that flows. What flows? Gases and liquids flow. So remember there's 4 states of matter: solids, liquids, gases, and plasma. 2 of them flow, and that are gases and liquids, and so gases and liquids make up fluids. So fluids are gases and liquids. And statics, no motion. So these are gases and liquids that are in static equilibrium. Nothing is moving. So in order to introduce us to some of the physics we can use to analyze fluid statics, we need to back up a little bit and recall some concepts that we've learned in the past, somewhere in our past. So one is density. Density gets the symbol rho. It's like a skewed P from the Greek alphabet. Rho is how you say this. So this is rho from the Greek alphabet. And what is density? Well, density is mass per unit volume. So this is mass per unit volume. So what symbol do we use for mass? We use M. What symbol do we use for volume? We're going to use capital V. Notice that I've put bars on top of that V because it's difficult to distinguish a little v from a capital V. So I'm going to put bars on top of my capital V. And you say, well, who cares? Little v is velocity, and I don't see it in here. Well, little v is actually going to be in the same equation as big V when we look at fluid dynamics. So we want to be very careful that we give volume a different symbol than we give velocity. So capital V. What kind of units are we going to have standard in the metric system for density? Well, the units for density are going to be the units for mass divided by the units for volume. Standard units for mass in the metric system, kilogram. Standard unit for volume, meter times meter times meter, or meters cubed. So a kilogram per meter cube is a standard unit for density in the metric system. Another quantity that we're going to want to remind ourselves of is pressure. Pressure is going to get the symbol capital P. And pressure is force per unit area. So pressure in symbols, force, symbol F, divided by area, symbol A. So force per unit area, and the units standard in the metric system for pressure are going to be the units for force, which are a Newton, divided by the units for area, which is a meter squared, and paying tribute to Pascal, who was a scientist that contributed quite a bit to the field of fluid statics and fluid dynamics. We're going to abbreviate this PA, but this is going to be a Pascal and abbreviated PA. So these are some quantities, both the density and pressure, that we need to be familiar with and remind ourselves of. I know that you've seen these somewhere in your past, and so here they are as a reminder. So now, fluid statics. So let's talk about fluids and how they behave and how objects behave when they're in fluids. So when we have a vat, let's say, and it has some kind of fluid of density rho in here. When objects are placed down, let's say we have a penny, and we place this penny down here in the fluid. This penny right here is going to feel a pressure due to the fact that it's supporting this cylindrical column of molecules above it. So there is a pressure due to the fluid in this vat that is above that penny. In addition, I could extend this column all the way up to the top of the atmosphere because there is additional fluid above this liquid that is in this vat. So we have two different pressures here that we need to think about. One is called atmospheric pressure. Atmospheric pressure is pressure that is due to the atmosphere that we live in, and it gets the subscript ATM, standing for atmosphere. If we're talking about standard atmospheric pressure, that is measured at sea level, dry air, and has a value of 1.013 times 10 to the fifth pascals. Remember, a pascal is just a Newton per meter squared, so that's the standard unit in the metric system. This is the pressure objects feel when they are at sea level in dry air, and that is due to the fact that they are supporting a column of molecules that is above them. Everything on the surface of the Earth is supporting molecules above them, and those molecules are the molecules that make up our atmosphere. So as we climb up from sea level to, for example, Albuquerque, which is about a mile above sea level, the atmospheric pressure drops because the column of molecules above us is a shorter column than when we are down at sea level. So atmospheric pressure varies depending on where you are. It also varies depending on how humid the air is. But anytime that we are going to be using atmospheric pressure, we're going to go ahead and use the atmospheric pressure that is measured dry air at sea level. All right, so atmospheric pressure is due to molecules that make up our air or atmosphere. Notice this penny is supporting this column of molecules that make up our atmosphere, but it is also supporting this column of liquid that I have further submerged the penny in. The pressure due to this column of molecules that are the further submersion of this penny is called gauge pressure. So gauge pressure is going to get the symbol P sub G, and this is due to further or additional submersion of an object in a fluid. All right, so I have another fluid here which I've been calling a liquid. You can see because the surface is contained, in other words, this doesn't expand out to fill the entire container. So this is definitely a liquid. Liquid drops to fill the container and has a defined surface level. So this is definitely a liquid, has some density rho. And this column of molecules above my penny is going to supply the gauge pressure. So the weight of these molecules divided by the area of my penny is going to give me the gauge pressure of that the penny is experiencing at its location. So the gauge pressure can be written as the weight of the molecules divided by the area of the penny. So this is the weight right here, and this is the area. All right, the weight of those molecules, how do we write the weight of those molecules? Well, the weight of those molecules is the mass of the molecules that are inside this little cylinder times the acceleration due to Earth's gravity, and then divided by the area. How can I write the mass of the molecules in this little cylinder? Well, I can write them as the density of this liquid or fluid in general. This particular case, we're dealing with a liquid. The density times the volume of this little cylinder times the acceleration due to Earth's gravity divided by the area. So the density and the volume make up the mass. So notice how it's very important that we understand how to manipulate the density mass volume relationship. We'll be doing that over and over and over. In addition, the volume of this cylinder can be rewritten as the area times the height. So I can re-express the volume as area times height. So the area times the height makes up the volume. And notice what's happened here is that I can get these areas to cancel out, and gauge pressure is just the density of the fluid the object is further submerged in times how deeply it is submerged in that fluid times the acceleration due to Earth's gravity. So gauge pressure always is going to be the density of the fluid that the object is further submerged in, how deeply that point is submerged, times the acceleration due to Earth's gravity. One more pressure that we need to be familiar with is total or absolute pressure. So total is going to be the same thing as absolute. Those two pressures mean the same thing. You'll see different resources defining them different ways. And this is just going to be the total pressure felt at a point due to all of the molecules being supported above that point. So that's going to be the atmospheric plus the gauge pressure. So total pressure or absolute pressure is going to be atmospheric pressure plus gauge pressure. So we really have three pressures that we need to be thinking about. We have atmospheric pressure. That's the pressure due to the fact that we have this column of molecules above us called our atmosphere that is being supported by every entity on the surface of the Earth. The value we'll be using for atmospheric pressure is going to be that is measured at sea level dry air. 1.013 times 10 to the 5th pascals. We also have gauge pressure. Gauge pressure is going to get the symbol P sub G, and that's standing for gauge pressure. And this is pressure felt due to further submersion. So this object is not just submerged in the atmosphere, but it is further submerged in some other fluid as well. And the pressure due to that other fluid is called the gauge pressure. The gauge pressure is just the density of the fluid that it is further submerged in times times how deeply it is submerged in that fluid times the acceleration due to Earth's gravity. Then there's the total or absolute pressure, which is just the sum of both of those pressures. It is the total or absolute pressure that a point feels due to the fact that it is supporting all of those molecules. So this gives us an introduction to fluid statics. We'll be using these concepts to derive some other physical relationships in the next video. So we'll see you then. Thank you.